Hello and welcome to this first press conference of this year's EGU General Assembly. And I'd like to introduce John Tarduno from the US. And this press conference will be about early Earth and early biosphere. John, go ahead.
Great, thank you. I'll start with just a few comments on the modern system. One of the things that we've become very interested in is taking a look at the modern system and really trying to figure out what the paleo system would be like, as we do a lot of this in the earth sciences. But in our particular specialty, what we're going to be focusing on, particularly in the session tomorrow, is the Earth's magnetic field. So what we see here is in a illustration from NASA is sort of a cartoon of the sun, and particularly a coronal mass ejection. And what we see is the Earth's magnetic field forming a shield, the so-called magnetosphere. And in particularly, this boundary is something that we call the magnetopause. So what's happening here is it's really kind of a pressure balance. The sun is basically losing mass, and streaming particles are forming a solar wind. And that solar wind is being blocked by the magnetic field, which forms this shield, as we can see here. That's the picture today, and we see this. I think everyone sees it when we have a really big coronal mass ejection. That is not everyone, but you see phenomena like aurora at low latitudes. So, for example, the last, or some of the most big storms of memory were in 2003, where we actually had auroras at low latitudes due to very large coronal mass ejections. That's a picture that we have today. What was that picture like in the past? I'll talk mainly about our part of the research, which is an experimental challenge, really, to trying to figure out the Earth's magnetic field part. And then I'll talk a little bit about the ancient sun. And within the theme of the session, of course, this is all very important, which I'll get to in the end, in terms of the preservation of the Earth's atmosphere, water on the planet, and the whole question of the habitability of a planet. So, first, without getting into too many of the technical details, let me at least give you a flavor for some of them. To look at the very ancient Earth record, we have a challenge as geologists and geophysicists, and that is we have rocks preserved, but these Paleoarchean rocks, the age that we're focusing on here, let's say older than 3.4 billion years ago, they've all been affected by later processes. We tend to think that these rocks have had a long and hard history. So they've seen later events, and we would like to be able to see through those later events to really understand the beginning part of the record. And the key here is that when a rock forms, generally an igneous rock, some rock formed from a melt and it cools, in the presence of a magnetic field, it can lock in a record of that magnetic field. That is, the magnetic minerals within that rock will lock in a record of the field. But that record is imprecise, particularly in very old rocks that have been reheated by these subsequent geological events. So our group at the University of Rochester has developed techniques. One of them is the beginning of which is shown here, is where we actually are looking not at a whole rock, but actually at individual crystals from the rock. And this is an example of a mount of one of these crystals. This might be a millimeter-sized crystal of, let's say, feldspar, that tend to record a more high-resolution record of the field that can see through these later events. We've also had to increase our resolution and developed magnetometer technologies. This is a squid, a three-component squid magnetometer, superconducting quantum interference device. What's unique about this instrument is that its bore is about 6.3 millimeters. That's the only one of its kind. that we are really trying to get the highest resolution we can at looking and reading this ancient magnetic field. So jumping to the chase here, what is shown here is a plot of our new data and actually the evolution of the field. What we see here are, in particularly in the colored symbols, are some of our newest data. Now we basically have records as old as 3.45 billion years. So we've pushed back the record of the Earth's magnetic field from some of the previously oldest data that we collected in 2007, about 250 million years back further into the past. So that's the first conclusion of our record. The second conclusion, of course, is simply that the Earth's magnetic field exists at that time. Now, that's an important conclusion for many reasons, and it's important because there are some scientists who believe that we perhaps did not have a magnetic field in the very early Earth. And there are various theories about this. This has to do with the cooling of the core. At this time, probably the core was entirely molten. There was no solid inner core, as we see growing later on. And it's possible that this very oldest core maybe was not producing a magnetic field. We simply don't know that. So that's why we're trying to push this back and get records older and older in time. This point here is just to illustrate one of these theories that there may not have been a magnetic field older back further in time. So these are our data that we have now. We have records that are suggesting that there was a field at 3.5 billion years ago that is a little bit weaker than we see today. The modern day field value is shown here by this black line. I talked in the beginning about this pressure balance. And here's that pressure balance. Now what we're looking at is the age of the Earth here. Now time is actually going forward in this direction. And here are our data sets again. And what we see here are various lines recording various geomagnetic field values as well as our data. And what I have on the vertical axis is something called the standoff distance. That standoff distance is just what it sounds like. It's how far is the magnetic field standing off the solar wind. That is, how far are we protecting the planet from the solar wind by the strength of the magnetic field. Today, it's about 10.7 on average Earth radii. What we're suggesting at 3.54, it's about 4 to 5, and this is actually a conservative model. I would say probably between about 3 and 5. That's a pretty interesting number because that number is basically equivalent to what we see in modern magnetic storms today. A big solar storm would actually produce that type of standoff distance. So that's the steady state conditions. Almost 3.5 billion years ago, we would have had this rather intense solar wind protecting. The Earth's magnetic field is still protecting us from that solar wind at this time, but it's not as efficient as it would have been, for example, today. So that's a graph. Here's a picture. If we wanted to imagine what the Aurora window would look like, this is sort of our vision of this. That basically we're looking at a huge auroral window where we basically have constant auroras at lower latitudes. This aurora window is now larger and actually allows particles to be penetrated down deeper into the atmosphere. So as I said before, some of the conclusions are that it would have been similar to the solar storms actually in 2003, something we call the Halloween storm, but that's the steady state conditions. This area of where we have the aurora is actually about 3 times larger than we see today. And it also suggesting that we're actually having some heating, expansion, and maybe some volatile loss from the uppermost layers of the atmosphere. Volatile loss meaning hydrogen, and if we're losing hydrogen, eventually we might be losing some water. So some of the important things to think about in terms of the broader picture here are, and on one hand, the Earth's magnetic field is actually very, very important to us in the fact that we've been able to push it back 250 million years. It means that it was actually there protecting us from the intense solar wind. And this is a very critical time because this is a time interval where we start seeing the first kind of tentative signs for life. So perhaps these things are actually linked together. It also suggests that even though it's there, it's not as efficient as it was, we think about it today. And it's actually hard to avoid there being some loss of some of these light elements. What that means in an evolutionary sense to us, and this is just speculation, but this is something that we want to follow up, is that perhaps this is suggesting that the Earth was much more water-rich very early on. Because if we, even with this magnetic field, if we are losing some of the hydrogen and water, that would suggest in an evolutionary sense the Paleo-Earth in its very infant state must have had more water than we think about today. So these factors, water and the generation of the magnetic field, to us are kind of linked in sort of developing a habitable planet, at least as we know it. So I should close by saying that my group at the University of Rochester has been involved in this research funded by the National Science Foundation. That's myself, Rory Cartrell, and Pavel Dobrovin, and Levi Newkirk. We've had great assistance by our colleagues in South Africa, Mike Watkins and Axel Hoffman, who have been key in helping us find the right outcrops, the right geological locations where we can actually see these very ancient records, as well as work by Eric Mamachek on early solar dynamics and David Siebeck in terms of solar-wind interactions. So with that, I'd be happy to take any questions?
Okay, thank you very much. Noah, are there any questions from the group?
Randy Shostak, reporter with EOS at the American Geophysical Union. You mentioned that there are some other scientists who don't buy into this. Can you tell me what their reaction, what their response is to your current research?
I didn't really mean to say that they don't buy this. What I think if, but certainly bring it up again if I'm not getting the point here. There are some different ideas suggesting that at times, even older than we're talking about here, the Earth's magnetic, there may not have been an Earth's magnetic field. And these are just theoretical models. There are actually two of them, one of which is by Professor Ozama from Tokyo. And his work is based on lunar nitrogen. He believes that there are, well, his measurements suggest that there are Apollo mission rocks that have nitrogen compositions that are unusual, and he believes they were actually derived, that nitrogen was actually derived from Earth's atmosphere. The way that this works is that the solar wind would actually erode part of Earth's atmosphere and then implant that nitrogen onto the moon. It's really a fascinating hypothesis. For that to work, there would be no magnetic field. So his idea is that about 3.8, 3.9, older than we're talking about, the Earth's magnetic field did not exist. There's another theory, completely different, by Stefan Lombroso and his colleagues, that has suggested that this has to do with the dynamics of cooling in the core. That in the very early evolution of the core, there was a boundary, molten layer above the core that actually was hot enough that actually prevented convection within the core. And he has suggested that older than 3.4 billion years ago, there may not have been a magnetic field. But his models are somewhere between 3.4 and 4 billion years old. So they don't really disagree with what we're saying. They're just, these are some of the ideas that are out there that suggest that there might not have been a magnetic field. Now, just taking advantage of your bringing that point up, if either one of those hypotheses are correct, what I've talked about here about the Earth being water-rich, that's an incredibly conservative statement. If those guys are correct, and there was no magnetic field in that very early time period, we might have lost as much as one terrestrial ocean's worth of water. So the Earth would have been much water-rich, much more water-rich. But, you know, these are the things that we need to test with more data.
Anyone else?
I just got a comment on the last. Sanjay Lamay, DPS Press Officer, Division for Planetary Sciences. I think I recognize that Aurora is from Jupiter, I think, right?
We've adapted it, yes.
Very good, thank you. Just want to point that out, that you don't really see it. But I guess my comment was, not a question, is that if you had even more water in the early Earth, wouldn't that make the question of where the water came from even worse than it is now, since we don't know where the water came from on Earth?
I don't think that's as much of as an issue, really. I do think that question is involved, yes. But I think in terms of the way that I look at it, if you kind of step back and, let's say, look at Spitzer Space Telescope measurements, and you look at how much water is actually in a terrestrial planet-forming region, there's plenty of water around. I mean, you know, there's enough water to get this type of water-rich planet, whether it happened or not. And I think the more detailed questions are, how do we lose the water and then satisfy some of the geochemical constraints and things along these lines. But in terms of having enough water being available, I don't think that's an issue at all. So.
Dagmar.
Dagmar Hörlich for the German radio station Deutschlandfunk. How was the sun behaving in those days, and how was the interaction between the Earth's magnetic field and the solar wind? Right. How did this evolve?
Right. So it's a good point. If I can just see if I can go back. It's not going to let me go. Yeah, sure. Let me go back. There are two ways to actually calculate this. So what this plot is, again, and this is a pressure difference, and we have one thing is the magnetic field values, but also what's embedded in here is, in determining this axis here, is how strong those solar winds are. Now, as opposed to the Earth, where the strength of the magnetic field is actually due to what we call buoyancy forces, convection within the core, the solar wind, its rotation rate. And the young sun is rotating much more rapidly than it would be today. And associated with that is a higher mass loss. So basically the sun is losing mass at that same time. So we believe that at the time interval of these data, for example, we're talking about higher, 10 to 100 times higher solar winds than what we see today. And we can calculate that. That's what these calculations are based on originally that rotation rate. There's also observational data that we can look at using solar analogs. Those are stars that we believe are similar to the sun but of different age. And my colleague, Eric Mamachek, also has done these type of calculations looking at X-ray emissions, and has found that these numbers may actually be conservative. The standoff distances, he would suggest, would be more down in this region. So that's the key factor here. Even if we have a field that is comparable or slightly weaker than today, we are still getting that boundary in between the solar wind and the magnetic field closer to Earth, because the solar wind is so much more intense as we go back in time.
Could you elaborate more on the link between the early signs of life and the magnetic field? And do you think that would hold true, or could there have been a magnetic field earlier, even in the Earth's history, 4 billion years, for instance?
Yeah. You've exactly hit the nail on the head. I mean, some of the earliest signs of life that have been reported are in the same rocks that we're looking at. Okay, and that could just be coincidence because of the function of the actual record that we're talking about. So we just don't know the answer to that question yet. All we have is the fact that there is a magnetic field at the time, and it just so happens that those same rocks are seeing, same stratigraphic rock interval, that is, are seeing evidence for these lives. There could have been a magnetic field earlier on, and perhaps life earlier on too. Yeah.
Dagmar.
What were the rocks that you're working with? Were these South African rocks or?
Yes.
Not the Greenlandic one?
What's that?
Not the one from Greenland, from EGU.
No. The key difference here is the rocks from South Africa have been heated to a maximum of 320 degrees Celsius, probably a little bit less than that. The Greenland rocks have been heated much higher, and that's the key difference. We basically need to find rocks that have not been taken to high temperatures, or they'll reset the magnetic minerals. Yeah. But within the area in South Africa, this is the Barberton Greenstone Belt, the Barberton Mountains. There were very particular rocks that we sampled that took a long time to find. Associated with these heating events are also chemical changes, so we have to find just the right type of rock that can see through this. And this particular rock was something called a dacite, was perfect for our analyses, but it took some time to find the right localities together. Again, this is really the work of our South African colleagues.
Okay. Thank you very much,
Okay.
John, for this first press conference. Thank you very much.
Yep.